Little Caesars Canadian deep dish slices and sticks for $7.99. All this to yourself? How un-Canadian. I'm ready.
Hi everyone, I'm Steve Brunton, and this is the first video lecture on a series I'm calling a boot camp on control, where I'm going to rapidly go through the highlights of optimal and modern control theory. So this is going to include how to write down a system description of a control system with inputs and outputs in terms of a system of linear differential equations, and then how to design controllers to manipulate the behavior of that system, how to design estimators like the Kalman filter so that if you had limited sensors you could reconstruct various aspects of that system. This is not meant to be an exhaustive, in-depth treatment of the subject, but really kept at a high level. And my goal is to, first of all, get you familiar with the major types of optimal and modern control theory. I want to teach you how to use these in MATLAB to actually work with a real system. And what I also want to give you a feeling for is what in control theory is easy and what's still quite challenging today, so that you can get up to speed on the real pressing needs of control theory today. Okay, and again, this is not exhaustive, so if this is really important to you and you want to, you like control theory and you want to go more into depth, there's deeper treatments both on the math side and on the applied design side. Okay, and so I want to give you just a little bit of perspective. I think about the world in terms of dynamical systems, so systems of ordinary differential equations in terms of the state of your system. And this has been an extremely successful viewpoint for modeling real-world phenomenon. Okay, so we model the fluid flow over a wing, or the popular spread of a disease, or the stock market, the climate, planets moving around the solar system. All of these are modeled as dynamical systems, and this has been a very, very successful framework to take in data from the real world and build models that you can use for prediction. But often we want to go beyond just describing the system event, to teach you how to use these in MATLAB to actually work with a real system. And what I also want to give you a feeling for is what in control theory is easy and what's still quite challenging today, so that you can get up to speed on the real pressing needs of control theory. theory today. Okay, and again, this is not exhaustive, so if this is really important to you and you want to, you like control theory and you want to go more into depth, there's deeper treatments both on the math side and on the applied design side. Okay, and so I want to give you just a little bit of perspective. I think about the world in terms of dynamical systems, so systems of ordinary differential equations in terms of the state of your system. And this has been an extremely successful viewpoint for modeling real-world phenomenon. Okay, so we model the fluid flow over a wing, or the population dynamics in a city, or the spread of a disease, or the stock market, the climate, planets moving around the solar system. All of these are modeled as dynamical systems, and this has been a very, very successful framework to take in data from the real world and build models that you can use for prediction. But often we want to go beyond just describing the system of interest, and we want to actually manipulate the system actively to change its behavior. And so that could be just imposing some control law, just setting inputs into that system in a certain pre-planned way to manipulate it. Or you could actually measure that system and make decisions based on how the system is responding to what you're doing. Okay, and so that's kind of the overarching view in control theory, is that you have some dynamical system of interest. Maybe it's a pendulum or a crane that you want to make more stable. You write down the system of equations, and then you design some control policy that changes the behavior of your system to be more desirable. Okay, so that's what we're going to talk about. And so I want to begin by just talking about the various types of control that there are. So there's lots of control that goes around all around us every day that is not active. It's called passive control. So I'm going to draw just a diagram of the different types of control. So one type that's very common, you see it all the time, is passive control. Okay, so for example, if you see a large 18-wheeler transport truck going down the highway and it has those streamlined tail sections, that's a form of passive control that's passively causing the air around the truck to behave in a favorable way to reduce drag. And if you can get away with passive control of your system, that's actually great, because you just have to design an up.
Then you have to design like an updated one. Just look at the transcript first of all. And he explains well. I know who Dr. Steve Brunton is. He's really good. Like he's really good. I want to see like he explain like what is going on here and stuff. Is it possible to explain slowly, like what is going on here? Like this slowly, calm down. Like first of all, how many sections are there for this pasted text explanation? So 8 major core sections. So introduction to control theory, the main ideas are the dynamical systems, inputs and outputs and whatever. So let's do one thing based on this abstract. Where's the abstract? So based on this abstract, is it possible to write a full latex code like with explanation and stuff? And then each section teach the coding part, and then each section teach the Python programming part, because this is for Python. So like what you have is like what you will have is the latex code with a summary math explanation, in correlation to the hypersonic missiles, followed by the Python program. Now, Python program, go for the general Python program because I want to learn. Okay. This is so during the hypersonic missile, it's fine. So during the hypersonic missile lesson, the velocity will be greater than 5 Mach. So the Mach is usually measured by whatever the speed of the rocket is divided by the speed of light. Small disturbances can produce extremely large trajectory deviations. The main disturbances will have like wind. Wait. Okay. The main Disturbances will have like wind gusts, thrust variations, aerodynamic uncertainty, air density variation. Traditional fixed guidance systems struggle because missile dynamics continuously change during the flight. And so the adaptive guidance system continuously will estimate the missile motion, the will update the aerodynamic models, will recompute the steering commands, will stabilize the trajectory. So few things to consider. So first thing first, the hypersonic missile will go at very high velocities, and the velocity of that missile will actually be larger than 5 Mach. And small disturbances means even a poke, even a touch would ruin everything. Now you must understand that if a touch ruins everything, and if a missile to fly in air, there will be many other disturbances that is going to automatically play a role, like subconsciously would play a role, like on the missile. We're gonna have like wind gusts because obviously it's going to be windy. We're going to have thrust variations where sometimes, let's say, the amount of thrust that is produced on the missile may be less, and so your velocity may decrease, or the thrust that is produced on the missile will be high, very high. It'll be exceedingly high, which is also a bad thing. You may think it's a good thing, but it's not, because if you have too fast, then you don't, you will not, you may pass the destination point. So if you want to hit on the enemy point, if you want to hit on the enemy point, then obviously you need to have certain amount of velocity. If you have less than that, you won't hit. If you have more than that, you won't hit because you went past that, right? So wind gusts, thrust variation, aerodynamic uncertainty. Obviously, you know what aerodynamic uncertainty is. Aerodynamic can be on drag force, on weight force, on the thrust force, on the nose pitch up, pitch down. So let's say if there's wind and then it went nose up, nose down. So you have it, variations of some aerodynamic values, right? So your pressure may decrease, or your pitch rate will decrease, or your velocity will decrease. Everything plays a role here, and the air density will also vary because obviously if you use a missile, now obviously it flies, right? And at some point in time, if you have obviously rho will be 1.225, that's like almost that's considered the base point. But you must understand you're using a hypersonic missile, so anything can change. So your aerodynamic density could be 1, or aerodynamic density could be 1.1, or aerodynamic density could be 2 here. So rare cases, but you never know. Anything can happen because at the end of the day, it's a hypersonic missile. The traditional fixed guidance system struggle because the missile dynamics continuously change during the flight. So the adaptive guidance system will continuously estimate the missile motion, update the aerodynamic models, recompute the steering commands, stabilize the trajectory. All those points, consider that that is one steering. And on that one steering wheel, what you're going to do is as it moves left or right or whatever, it's going to fix all the things. It's going to fix the aerodynamic uncertainty. It's going to fix the missile motion. It's going to fix the steering commands. It's going to fix the trajectory. Everything plays a role here, right? Everything plays a role. And so we're going to have like one black box that is going to compute everything. Cool. Hypersonic missile. So the missile star vector becomes x is theta and omega, theta being the pitch angle, omega being the angular velocity. So if I were to say that, okay, it's going to go up, the the velocity of the missile, let's say, is moving at 30 meters. No, not 30 meters. 50 meters per second. 50 meters per second. So 1 second, 50 meters. Very fast. So 1 second, 50 meters at 30 degrees angle. So your angular velocity is 50 meters per second because it's moving at 50 meters per second, but at an angle, right? It's not moving at, like, obviously, usually it's moving straight forward, but it's also moving at an angle. Now, obviously, you know what a slip up angle is, where the difference between the original original direction of where the missile should go and the original direction of where the missile is going, the difference on that angle between the angle between these two, there is a slip up angle. I'm pretty sure you know what a slip up angle is. So we can do the programming actually. So input numpy is np, theta will be np dot radians 5, omega will be 0.002, np dot array theta omega. Do we have Visual Studio Code here? I don't need Visual Studio Code. I have Google Code. I'm gonna have import numpy as np, import matplotlib pyplot as plt. And the first thing, obviously, I'm gonna set the np.radians 5. What does np.radians 5 mean? Oh, 5. 5. Is it 5? That's 5 radians, right? If I write theta, just wait. Theta is equal to np.radians 5 print theta. Five decrease, right? So it converted. So this converts from theta to radians. Now if omega, I'm not going to write omega. I'm going to write angular velocity is 0.02, and so then I'm going to have the state vector. State vector would be np.array. We're going to have theta, and we're going to have move. Oh, come on. I can't even omega. And then finish it with a bracket. Theta is there, and that's not omega, that is angular velocity. Do I bracket? Oh, I have two of them. Okay, we good. So what we did so far is that, so far I'm just going to note down. So far what we did. Obviously import the numpy module, the numpy module to create changes, to create arrays for more than one values if you want to create matrices. So that's also important. Import the numpy module for values change and adjustments, like using matrices and state vectors and whatever. Getter angle. So whatever angle you have. Now the only reason I said 5, I know 5 is given here, but 5 is also a danger zone. 5 degrees change for first of all, like anything that's considered with aerospace, like rocket or a missile, they don't usually measure in degrees, they measure in radians, because the computer will be able to understand radians easier than the degrees, because obviously you also have temperature in degrees, you also have Fahrenheit in degrees, and if you do degrees, it may not be able to calculate well. In some cases, maybe, but in most cases, no. Although, yes, you're going to get an output in degrees, but the module, like the AI model inside that black box is going to measure in radians. It can read radians, it can understand radians. Obviously, it's going to do the binary and the hexadecimal and all the stuff, but it's for them, it's easier to understand anything in radians, not in degrees. So whatever value we have convert that to radians. And then we got the state vector. State vector in correlation to the pitch angle and the pitch angular velocity. And then print it. Yeah, we already did it. So what's going on here, obviously? So what's going on here is that we set the theta to 5 degrees. Now, realistically, it will be 5 degrees, because I mean, you may think that 5 degrees is less because that's in terms of the rocket, not the missile, but the rocket. If rocket has 5 degrees change, that's completely fine. It doesn't change as much. Although it is also very good to take into consideration that 5 degrees change is also very dangerous. But in a hypersonic missile, yeah, 5 degrees means you need to look onto it. You really need to look onto it. So state space model. So the missile dynamics will become x dot is equal to ax plus bu plus d of t, where a is the system dynamics matrix, b is the control matrix, u is the control input, d of t is a distance. Suppose a being 0, 1, minus 4, and minus 1.5. This matrix will, so we can actually do that. A will be np dot array 0, 1, minus 4, minus 1.5. Okay. And B will be np.array 0, 1. So this means that if I were to print A and print B, then obviously I'm going to get 0, 1, minus 4, minus 1.5, and I'm going to get 0, 1. So good thing to learn about these NumPy modules. So how to create a 2x2 array? First of all, obviously you need to at A is equal to np.array. If you want to create a 2x2 matrix, then you have to have, obviously, first of all, you need to have 2 boxes, so 2 square boxes, right? And followed by that, you are going to create, if you want a 2x2 matrix, then you need to have 2, 2. If you want to create 3 matrix, then 1, 2, 3. And if you want to do 4, 1, 2, 3, 4, right? If you do 4 of those, and then you're gonna, like, if you want to 1 and 1, obviously 1 1, there is also a matrix, but that itself is a value. So you have a value inside a matrix. Because for example, here I have what you call 2 rows. 2 rows, 1 column. So 2 1, right? So wind gust disturbance model. So suppose the wind gust appears that the fact that d of t is not equal to 0. So disturbance does exist, right? The disturbance will exist. And if the disturbance were to enter the missile dynamics, then suppose the disturbance forces will become d of t is equal to 0 at 0.4. This disturbance will affect the angular acceleration dynamically. And obviously, for way to write 0 and 0.4, I'm just going to write d is equal to np.array 0 and 0.4. Then if I were to print d, then obviously I'm going to get the matrix. So this matrix, the only reason we write 0 and 0.4 is because this shows that it is not 0, but at the same time we're focusing on a matrix, and the lowest matrix, the lowest value we can focus in terms of a matrix which satisfies that x dot is equal to ax plus bu plus d of t, where d of t is also represented in a matrix form. The lowest I can go is 2 and 1, right? Because if I say d of t being 0.4, we can, I'm not saying we can't, we can, but you must also consider that other factors will also play a role. Because specifically, rather than going for 2, we would actually have to go for, for example, let's say we said 4, right? So 0, 0, 0, 0.4. Disturbances can be anything. It can be the wind uncertainty. It can be the it can be the wind uncertainty. It can be the what do you call, oh god, thrust uncertainty. It can be the thrust variations. It can be anything, right? It can be anything. Cool. All right, cool stuff. Thrust vector control. So the control input will become u of t being the delta of tvc. The tvc rotates the missile nozzle. This changes the thrust direction dynamically. All right, so the thrust vector control, so the control input will become u of t being the delta of tvc. Delta of tvc is obviously, we have learned this before, that is the derivation in correlation to the thrust vector correction, thrust velocity correction, not thrust vector, thrust velocity, thrust vector control, thrust velocity correction. Long story short, if I were to see that I have an error, so let's say, for example, my desired, I don't know, my desired pitch angle was, I don't know, 3 degrees. Let's say for my missile to, let's say, hit the enemy destination, then I must say that my initial pitch angle should be 3 degrees. So my desired angle is 3 degrees. But okay, I now begun the launch. Now the missile will start launching. It's going to go. On the first few seconds, you saw that, okay, it didn't go 3 degrees. It went 7 degrees. Then you're going to say, okay, it went, your desired is 3 degrees. Your desired was 3 degrees, but the original went up 7 degrees. So which means you actually have an error of 4. And so they're going to automatically, what it's going to do is that it's going to measure based on how much thrust do I need, how much velocity do I need, how much pitch angle do I need to slow down or lower down to ensure that I'm not losing much more fuel, or I'm not increasing more fuel, like I'm not unnecessarily changing the fuel, but at the same time, I'm also able to, it won't be exactly 3 degrees, but at least I can say closer to that, right? So it's not going to go directly to 3 degrees. So it's going to be like 7, then 6.7, 6.6, 6.5, so on and so forth. And because the difference between the two values is less, the time it's going to take is like probably 1 second. But obviously 1 second is, you know, dangerous. So our main aim is to ensure that it dives deep, like it lowers deep, but at the same time it doesn't go too deep. There's going to go 3 like instead of going from 7 degrees to 3 degrees, it'll go from 7, like instead of going from 7 degrees to maybe 1 degrees, it's going to go from 7 degrees to maybe around like 3.4 or 3.3, something like that, right? That's what our main plan is. So the TVC will rotate the missile nozzle. This changes the thrust direction dynamically. Suppose the feedback control law becomes U is equal to minus kx, where k is equal to 12 and 4. Now the closed loop system, so let's say k is equal to 12 and 4. So this is your feedback control matrix. So let's say k is equal to 2 and 4. Closed loop system will become a minus bk of x plus d of t. I still did not understand number 5. I still don't understand number 5. Oh, I have it here. I still don't understand number 5 though. Like, can you explain it again? Like, what's going on? Can you explain it again? Like, what is going on? Dude, okay. Okay. Okay, we get it. Okay. Nope, I am not going to defend. and hit post. And hit post. And post. All right. So missile starts rotating. So suppose the wind pushes the hypersonic missile upward. So let's say that it'll push the hypersonic missile upwards, right? The missile pitch angle changes. So mathematically, the pitch angle will obviously increase. So this means that the missile nose is no longer pointing. So long story short, if I were to say that the theta is like maybe the my desired theta will be 3 degrees, I'm gonna say that okay, theta is 3 degrees. Cool. Theta is 3 degrees, right? And obviously after the launch, what he saw was okay, the sensors measuring the estimated position of where the missile exists. Then I'm going to say okay, it is 7 degrees now. So obviously the pitch angle increase. So missile, the nose of the missile is no longer where it should be. It increased. So obviously the trajectory will become deviating. Instead of going towards the enemy location, maybe it may go somewhere else. Maybe it may reach. Maybe it may reach to the enemy location. We don't know. We don't know. But it may not be accurate. Right? So the state vector stores the missile motion. So we have the x being theta and omega. So it will store the theta is going to store the omega. So the initial one is the desired one, right? So it will be, let's say, 3 degrees and I don't know. Okay, initially it's probably 0 degrees, right? 0 meter per second. So obviously there is none. Now the first, not the initial one, but the first time step. So let's say state vector one. Let's say 7 degrees and 500 meter per second. Like anything can happen, right? So let's say 500 meter per second and 3 degrees. So controller will read the missile state. So it's gonna store all those values inside one state vector x. So every single time it moves, so it's like paint, right? So when you go to paint, and then you're gonna see this matrix, right? It'll keep on. I don't know if you have there. Look, it keeps on changing, right? So it's gonna keep on changing. Now here's the most important question: U is equal to minus kx. So this equation means that using the current missile motion, use the current missile motion to compute the correction. So you saw that k is equal to 12 and 4. So they determine how aggressive. So 12 reacts to the pitch angle, 4 reacts to the angular velocity. One question: why is it 2 column 1 row? So what does K refer to? And okay, so that's the feedback gain. Okay, one question. 1 minute, 1 minute, 1 minute. Step 5, 6, and 7. The negative sign, without negative sign, it's going to push it more upward. You don't want to push it more upward. You want to act it the opposite way. Okay, step 5, 6, and 7. Can you explain again? Can you explain again? What what matrix does K play and what matrix does X, the state vector, play? Oh, here you are what? Oh, I get it. I get it. You are 57th man for Valentina. Calm down. So we have u is equal to minus kx. So two major objects, which is the x and k, they do completely different jobs. What does the state vector x do? So x is theta and omega. So it's called the state vector. So it will store the current missile condition. It's going to store the current missile motion. And in the hypersonic missile, the first state will be theta. There's the pitch angle. The second will be the angular velocity. That's the missile rotational speed. So the rotational speed and the pitch angle. The x is technically what it's doing right now. It's going to go up. So let's say, for example, okay, what is rotational speed? Does the missile rotate? Oh yeah, it does rotate. It does rotate, yeah. So it's like, let's say, for example, it says 7 degrees. It's like moving, right? That's literally x. X is literally like what it's doing right now. So if I go to paint here, I moved, right? So 560 to 195. So that's x. That's x, 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 x. Right? It's going to keep moving, keep moving, keep moving. So every single thing is measured. Every millisecond, every second is measured. So suppose x is 0.1, so theta is 0.1, and the velocity is 0.05, meaning the missile nose tilted upwards. 0.1 is big. In a hypersonic missile, 0.1 is big. Like 0.1 in hypersonic missile is like 10 degrees in an airplane and 5 degrees in a rocket. So 0.1 is big because hypersonic missiles are very prone to being sensitive. So if I were to touch, even if I were to touch a little, boom, it's going to deviate everywhere. So the missile nose will tilt upwards, and angular velocity means the missile rotating upwards slowly. So the state vector is not controlling anything, it's only storing the information. The controlling part is the u of t, the thrust vector thing. This x is only for storing. So k, what does k do? So this is the feedback gain matrix. So its job is how strongly should we react. So obviously they're going to go with the highest values first because it makes it safer. Because if you go with lower values, I mean, they won't go too high values, but then one question. Step 6. Going for too high values can also cause error. And going for too low values also cause error. Then how do they know what values to pick? Controller tuning. Yeah, it's huge, yeah. Because um the dynamic pressure will be extremely large, because then if I were to have extremely small values, then it's going to go smaller, because v square of 0.1 is 0.01. V square of 500 is what? So 500 times 500, 250,000. So that is really dangerous, right? And so we need, so how do they pick the, but is there a way, like, can we, x dot is equal to a minus bk of x. So engineers choose k. So the system eigenvalues become stable, meaning no oscillation, fast response, stable motion. And then LQR, this is huge for aerospace systems. Instead of manually guessing the gains, the computer will mathematically compute the optimal using the optimization. LQ, oh shit. Okay, calm down, calm down, calm down. Calm down, calm down. Um, okay, slowly. How do we fix it? What's going on? How do we fix it? What's going on? What's going on? Slowly, please, slow down. Love him. Love him. Marry him. Oh my god. Oh my god. Oh my god. Valentina. Oh my god. Oh my god. Oh, he's so cool. He's so cool. Valentina, go marry him. What profile picture is that? I don't know. That's cool, dude. Oh my god. Oh, I'm hurt. Oh my god. Tina, what the fuck are you doing, man? So cool, dude. Yeah, cool, dude. Oh my god. Oh my god. Oh, you roasted me, big man. You roasted me. Oh my god. And hit post. All right. Can we write a Python program for it? Okay, explain what he just explained. Explain what he just explained in latex code. Oh my god, you insulted me. Very good. Ho ho and hit post. And hit post. Yeah, my mom knows her. Anyways, explanation. Let us add it here. Yes, my mom knows her. What? Now let me. No, calm down. Oh, okay. Someone followed me. I didn't. Everyone, who are you? My doctor or what? And hit. Oh, she's gonna reply to everyone. Everyone. She'll reply to every single person. She'll reply to everyone. Change your bio, change your bio, then change your bio. Go, 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 go. Change your bio, change your bio. Go, change your bio. What are you doing? Change your bio, go, go.